Okay, so we did sat solving last week, which is to do with propositional logic, and that's an important and useful practical problem that where one formulates problems to be solved in propositional logic, submits them to a sat solver, and the sat solver finds solutions for you. Today we're going to look at the more expressive logic, predicate logic. We're going to look at a range of, so today's topic is algorithmic problems. A range of problems that occur in predicate logic. And part of the goal today is to just talk about what one can do in predicate logic, because it's much more expressive than propositional logic from an algorithmic point of view. But a lot of the results we're going to cover are in a sense theoretical, because they say, for example, something is not possible. So we can't solve the problem algorithmically. But at the end, we'll go to a particular problem that is solvable in a more, well, two problems that are solvable in one in a very practical way called model checking, and another in a more or less practical way called bounded satisfiability. And those two problems relate to practice, and they will relate to the student presentation in 3 weeks' time on the alloy analyzer. So for those of you who are giving a presentation in 2 weeks' time on SMT solving, that material I'm going to cover in next week's lecture. I actually reorganized the material because I realized I got more material for this week than for next week, and also it makes sense to do things in this order. But nonetheless, so the people doing a presentation in 2 weeks will not have material from the lecture today, but nonetheless, I will put links for you to do background research and to look at the material. I'll put links on the page this afternoon, so you still have the 2 weeks preparation period. And in some ways, it's good like this, because when we cover the material next week, you'll be in a better place. You should be in a better position to appreciate it. Anyway, it is what it is, and it will sometimes, it's sometimes going to be the case that the student presentations cover material that is presented only in the, that's related to material that's presented only in the lecture the previous week, rather than 2 weeks before. But you'll still always be given 2 weeks of preparatory material. Okay. Any questions on that? No. Right. So predicate logic was something we covered in an early lecture, both in its own right, with its own syntax, and then how we subsumed it into type theory. Today we're going to go back to looking at it in its own right. So I'll remind you of the language of predicate logic. So a language of predicate logic is determined by signature, and the signature consists of a set of relation symbols or predicates of, this is a curly P of relation symbols. So we sometimes call them relation symbols or just relations, or we sometimes call them predicates. They mean the same thing. And the set, maybe I'll make it a bit less curly, but anyway. And a set F of function symbols. And just to keep things brief this week, I discussed a few weeks ago that constants, things called constants, can be considered as function symbols that have zero arity. And just to make things convenient this week, I'm going to do that. So including constant symbols. And a predicate symbol is going to be given a letter or some symbol for the predicate. And we have, so this will typically use P for such a thing, a predicate, and it has an arity. That's the number of arguments it expects. So we specify the arity, and that will allow that to be 0. So predicate symbol of arity 0 is like a propositional constant, if you like, or propositional variable. A higher arity, it's like a relation of that arity. And so also function symbols also have arity. And using the predicate function symbols, we define the language. Oh. Well, the whiteboard is disappearing on the video.
I'm to argue. Right, I don't want to spend too much time on the lecture. Just trying to think of something I can say without the whiteboard.
Almost there.
Okay, thank you.
Yes, now it's much better. Thank you.
You're on Zoom.
Yes, I fixed my microphone.
Oh, and actually, the way the screen's flashing just reminds me. So thank you for that interruption, because I actually forgot to spotlight the video. So let me do that. I'm sorry. This is today's technical issue. Oops. Right, that should be better. Okay, so then we have the language of formulas, where a formula, we might remember, the grammar symbol specifying a formula is either an atomic formula, which is the predicate, followed by the right number. So we have the arity P number of arguments. And in these positions, we have something called terms. We'll allow ourselves to say 2 terms are equal, and then we'll have the usual propositional connectives. Anyway, I'll just use those ones, but I'll often write an implication. Finable, and importantly, we have the quantifiers. Universal and existential quantification. And terms are defined by a grammar that they exist the variables and also instructions where we apply function symbol to the right number of terms. And this is arity of arity. A constant symbol is a function symbol of arity 0, and when we have a constant symbol, we don't need to give it any arguments at all. And it's more expressive language than propositional logic, because we have the quantifiers. So an example signature. I mean, we did this sort of thing a few weeks ago, but I want to build on this today. So an example signature would be to include, say, binary relation symbol, and often rather than write it as a set P of relation symbols and a set F of function symbols, we'll simply just list the ingredients in the signature. So here, this is a relation symbol, relation arity 2. 0, that's a constant. In other words, a function symbol of arity 1, and a plus. We'll just have. So this is the little language that allows you to talk about 0 and addition, and you can't say very much, and an order relation. And then we'll have formulas that we can define from this. So here we have the formulas, terms. So an example formula here would be for all x, 0 is less than or equal to x. That's the formula, and the point of, and this is a special kind of formula. It doesn't have any free variables. We did free variables and bound variables also a few weeks ago. So here the only x is bound. So a sentence, this formula is what's called a sentence. Formula with no free variables. And the point of the sentence is it should be either true or false in any specified interpretation of the symbols. But it's clear you have to specify an interpretation of the symbols in order to determine whether it's true or false. Because, for example, if we take the natural interpretation of these symbols in the natural numbers, which, because we're computer scientists, we think of as containing 0, then this is true. And this is true in the interpretation in the natural numbers. I say the natural interpretation because the natural interpretation is the one in which this is interpreted as the expected less than or equal relation. This is interpreted as 0, and this is interpreted as addition. But these are just symbols. We could give another interpretation in the natural numbers. For example, we could perversely say that this is interpreted as equal, that this constant is interpreted as the number 17, and this binary operation is interpreted as the exponentiation operation. Nothing's stopping us saying, let's consider that interpretation in the natural numbers. And under that interpretation, this formula is false, because it's saying every natural number is equal to 17. True. And there's, of course, another example where it's false is that it's false in the natural interpretation in the integers on the real numbers. So the role of these interpretations is fundamental in determining whether or not a sentence is true. And what we need to. So it's important to understand what we mean by an interpretation. In these cases I've given, it's quite intuitive, but there's actually a mathematical definition of what you need to interpret the symbols. And this is something called a structure, or in the Huth-Ryan textbook, it's called a model. So a lot of what I'm doing today is in the Huth-Ryan textbook, so you can refer to it there for more details and a lot more explanation. So I'm going to call such things structures. But in the Huth-Ryan textbook, or models. And what a structure is, it's the ingredients we need to interpret the language we've got. So our formulas are going to say things like, this. So we're quantifying over some set of things for all x, well, x in what? So in the previous lectures, when I was unifying with type theory, we were quantifying over elements of a type. And now I'm going to just standard first order logic, standard predicate logic, where we leave the set of things we're quantifying over implicit in the syntax, but we make it explicit by talking about the structure we're interpreting it in. So the structure gives us the domain of quantification of the universal and existential quantifier. And we also need to say what the symbols mean. So structure So typically one writes a curly M for structures. So M stands for model here. Often use a curly symbol for the structure. And what it is it's a structure, a mathematical structure that has various components. It has a set. So M is a set. And the convention I and many other people in logic use is that when you name a structure with a curly uppercase letter, like in this case M, you use the same letter in non-curly font, so just ordinary font, but still uppercase for the set associated with it. So this is the set of elements over which the quantifiers will quantify. And then we have a collection of, I'm going to write them as P subscript M for every P in curly P, for every predicate symbol P in the set of all predicate symbols. And we have a collection of, we write them as F subscript M.
Subscript is or set M.
So the subscript is curly, but actually, let me just check with my notes whether I use subscript or superscript. Yeah, I do. Actually, in the notes, I use superscript. So that's. And what these are the mathematical. So there's one of these for every function symbol, the set of function symbols. And these are the mathematical specifications of how we're interpreting these predicates and these function symbols. So N is a set, and this is called the domain or universe quantification. And for every function symbol, let's do the relation symbols first. So for every relation symbol, P of arity N, its interpretation, P sub M, is a function that maps n tuples of elements of the universe to the set true and false. So it just gives them truth values. So I think in my notes I just use little t and f, and maybe this is this. Yeah. And for every function symbol f of arity n, it is interpreted as an actual function that works, that sends n tuples of elements of the universe to an element of the universe. Okay, so function symbols represent functions on the universe, predicate symbols represent, this is one way of encoding relations of the universe. Send every tuple to the truth value of whether the relation holds or not. Okay. So for this signature here, you can for yourselves work out the actual mathematical definition of the interpretation which the natural numbers and the interpretation in the integers, I'm going to give you a different interpretation of these symbols by specifying a structure for this signature as an example. So an example structure for the above signature. So notice that the structure is determined by what a structure requires is determined by the signature, because you need to have an interpretation of every predicate symbol and also of every function symbol. So an example structure for the above signature. So we need to give a set we're going to interpret these relations in. And so my example structure is going to be set. So let's call this curly L. And the lists. And then L. So we need to say what the underlying set is. And the underlying set here is going to be lists of natural numbers, or a more mathematical way of saying that is finite sequences of natural numbers. So I'm just, there are innumerable possibilities for different mathematical structures we could give to this language, just different ways of interpreting these symbols. And I'm just giving you one as an example of what we need to specify. So I guess you're in Ishirama. Do people use this notation for the set of finite sequences of elements of the set of natural numbers? Okay. So now our underlying set is the set of sequences of numbers, or lists of numbers, if you like. And we're going to give the natural interpretation of these symbols in this structure. So the interpretation of 0, the constant in the structure L, well, that's a zero-ary function. So for a constant, we have a zero-arity. So the interpretation would be a function from n to the power of 0, which is just a singleton set. So normally we just say that the interpretation of a constant is just an element of the set. So that's the intuitive interpretation of a constant. We want to interpret this as a relation on the set. This is an element of the set, and this is a binary operation of the set. So what's the natural interpretation? I mean, there are many unnatural interpretations again, but what's the natural interpretation of the 0 element in the list of sequences? The empty list, or the empty sequence. So if we were writing it as a list, we would say nil. But there's a standard notation for the empty word, which is this like curly epsilon, curly little epsilon. So this is the empty sequence, the empty word. And then plus is going to be a function, a binary function. So it's going to take two words. It's the function that takes two words as input and maps them to what's a natural binary operation to do on two sequences. Concatenation. So I'll just write it like that. Concatenation. Okay, so this is, or often if we're writing this, we'll simply be defining a function, so we'll just say what it does on its arguments. And we'll just write it like that. Okay, so is that clear? We're specifying the set of things we're dealing with. We still need to define the relation. So in this case, less than equals is going to be a function that takes two words and says true or false. And what's the natural interpretation of a less than equals relation on words?
Lengths.
Sorry?
Lengths.
Oh, okay, that's one. Yep, so one would be the length of the first word is less than or equal to the length of the second word. We could use that one, isn't it?
Element-wise.
Element-wise, yeah, so there's a name for this. And so what I'm thinking is what's called the prefix order.
Oh, yeah.
So this will map to true if W1 is a prefix of W2 and false otherwise. Yeah, so being a prefix means the word W2 starts with the letters of the word W1. Actually, I'm going to change this. Binary words are kind of more computer science, fun in computer science, so that's changed. It doesn't make any difference. I mean, we had a perfectly good interpretation words of the natural numbers and a perfectly good interpretation of binary words. Okay, and once again, so the official interpretation of less than equals is this function here. But again, we would normally write this as it would be specifying. So this is the interpretation of plus in L, less than equals in L. We would normally write this as we're specifying that W1 in L is less than equal to W2, if and only if W1 is a prefix of W2. With this interpretation, can anyone think of a sentence that's true for this signature if we interpret it in the natural numbers, that's not true for this signature if we interpret it in this structure of words? Just some sentence that distinguishes the two. So I'll let you think about that. Well, commutativity of plus. Very good. That's exactly the one I was going to do. So the sentence for all x, for all y, x plus y is not equal to y plus x, holds in the natural numbers. Now, by the natural numbers, I mean the structure associated with the natural
Not equals.
Oh, sorry. Equals, yeah. Holds in the natural numbers. Well, I mean the natural interpretation in the natural numbers, but not in 0, 1 star. Okay. But the question is, how do we know this? Well, let me actually give a name to this structure. So by the natural numbers, I mean interpreting the symbols in the way we intend in the natural numbers. So this is the natural structure on the underlying set of the natural numbers. The one where we interpret 0 as 0 plus addition and less than equals as the expected order relation, but not in so. This was called curly L. But how do we know? I mean, in this case, it's hopefully obvious that this sentence holds in the natural numbers, of course, but it doesn't hold here because you can find two words that if you concatenate them different ways around, you don't get the same word back. But what we're saying here mathematically is we're saying that the structure N for the natural numbers satisfies this commutativity formula, but the structure L for lists does not satisfy this commutativity formula. So we need a relation that relates structures M to formulas, or actually to sentences, and this we read as M satisfies phi. So M enjoys the property phi. So the natural numbers structure enjoys the property of commutativity, it satisfies commutativity. The list structure with concatenation as the operation for addition does not satisfy the property of commutativity. So in order to make mathematical sense of this, I mean, we hopefully see intuitively what's going on. We need to give a mathematical definition, and this is now very important, and this is what we're going to end the hour with. Going to define what's called the satisfaction. And the satisfaction relation is of the form M. The structure satisfies the formula depending on some interpretation of three variables in the formula. So M here is the structure, and this row is an environment, which is simply a function mapping variables to elements of M, elements of the structure, of the underlying set of the structure.
Excuse me,
Yeah.
I have a question about terminology. So is the structure together with the environment called a model?
It depends who's talking.
Yeah, no, so in this, for our purposes, we will call this a model, or we use something like that.
So for me, a structure is a structure, and what I would call a model is a structure that satisfies some specified set of sentences called a theorem. So then you have a model for a theorem.
Yeah.
That's what I would call a model. But in some cases, in general, but in some cases, and I depart from that, in the book they use the word model to mean structure. And models structure has a precise meaning, I think. Model is a sort of word that can be used a little bit to suit what one currently wants to do. So it can change meaning depending on who's deciding what the terminology means and the context you're using it. So the reason for needing an interpretation of variables is because, for example, in this structure L, you can ask, does L well, you could ask, does X less than equal to Y hold in L? And of course, that doesn't really make sense because we don't know what X and what Y mean. But if X is a variable, so we are allowed to interpret it as a list, and Y is a variable, so we're allowed to interpret it as a list too. So that's, that we can't really make sense of, but we can say that L does satisfy X equals Y if we map X to the word 0, 1, and we map Y to the word 0, 1, 1. Then that would be true, but L does not satisfy Y less than equal to X if we make the same assignment. So, or let's change. Let's keep the formula the same. The point is, the truth of the formula or not depends on what values we assign to the three variables. So if we map X to 0, 0, 0 and Y to 0, 1, 0, 1, then this would not hold. Then x is less than x is no longer a prefix of y. Okay. So the satisfaction relation is defined by basically interpreting the formula phi and reading down the reading the conditions for which we would expect it to be true, and just converting that into a mathematical definition. And one thing we can think of is, we can almost think of this as an algorithmic process of, we want to check that the formula is true in the structure M. It may not be very practical because the structure might be infinite, but in the case that we've got a finite structure, it will turn out to be practical. As we'll see later. So basically we need to go down the different cases of, consider all the different cases for the formula. So it might be an atomic formula in which we've got the form, a relation holding to it's a relation symbol applied to the right number of terms, and this we say this is true. Sorry, we're interpreting it in some. This is a function mapping variables to elements of the universe. So for this to be true, this holds if and only if the relation, our interpretation of the relation symbol in the structure, if we apply it to the interpretation of the terms in the structure, I've got under the interpretation of three variables rho. So here we were just interpreting of variables, so we just interpret the variables, the elements of the structure. But in general, when we have an atomic formula, we've got terms here, and now we need to define how we interpret a term. Well, a variable in rho, let's omit the n here, just to make things a bit. But we're interpreting everything in the structure n. So variable in is interpreted by the environment simply as value that the variable takes. So the value in the set that the environment maps it to, and a function symbol applied to some terms. This is interpreted in the environment rho by taking the interpretation of the function symbol and recursively working out values that the terms get assigned. Okay. And similarly, we've got some equality between two terms. This holds the structure satisfies an equality if and only if the term, the element represented by T1 under the environment rho is the same as the element represented by T2. So we interpret T1 according to rho, and we ask for it to be the same as interpreting T2 according to rho. And then for propositional connectives, I'll just do the case for conjunction. That we've got a conjunction of two formulas. Well, this is true if and only if. So now we now get to a sort of quite routine case of basically interpreting what the formula means. When does it mean that M satisfies both phi1 and phi2? The conjunction phi1 and phi2. Well, that holds obviously that conjunction means conjunction. So if and only if we define it to hold if and only if M satisfies phi1 and M satisfies phi2. Disjunction, place that with or. Negation, you do. Yeah. The negation holds if and only if the formula underneath it is not satisfied. And then the interesting cases are for the quantifiers. And maybe I'll just write the for all case. And basically, the exist case is, I'm going to write it for all in English here, and the exist case is dealt with by replacing the for all in English with a there exists in English. So we want to work out when is it appropriate to say that for all x, phi holds in the structure M. Well, that means if for that we want to say that phi holds for all elements x of the structure M. So we want to say for all elements, let me use A, the elements, just to distinguish them from the logical variable x. But for all elements A in the structure M, what we want is phi to hold for that element A. What does phi holding for that element A mean? Well, the element A is the value we're taking for x. So we want phi to hold if we update the environment by redefining its value of x to be x. So we ask for all A, phi to hold in the environment row where we need to use this. Let me just check the notation I'm using in the notes. So we take the environment row, but we're going to use this notation. We update the value of x by, so this is the new function from variables and values that behaves the same as rho on the variables different from x, that maps the value of x to A. How many of you have seen the satisfaction, some definition of satisfaction, maybe not exactly using these environments, but have seen some definition of satisfaction for predicate logic before? Okay, not that many of you. So it's the sort of thing that is actually quite straightforward, but it can look very awkward when you first meet it, partly because you're defining things in terms of themselves. It's something you need to get your head around, and I'm not going to spend more time in the lecture talking about it. So for this lecture, there are handwritten notes, and there's also one LaTeX slide that has this definition nicely written up on the satisfaction relation. If you're stuck, if you find it perplexing, please look at the Huth and Ryan textbook and try and understand the notion of satisfiability in logic, because it's very important to the course.
Excuse me. The first definition was, I think, given that P M is a function, we should have equals to.
Yeah. Good. Yeah, we defined it to be a function that takes truth values. That's very good. Okay, it's 2 minutes past, so we'll have a break until 10 past, because we're having short breaks in order to. Okay, so we have the notion of structure in which we can interpret the signature we've got of predicate logic, and we can do this in different ways and in different structures. The interpretation might lead to the same sentence getting assigned different truth values. But this is completely analogous to when we have a formula in propositional logic. If we have a different interpretation of the propositional variables, then a formula may change its truth value depending on the interpretation of the propositional variables. But in propositional logic, it's very important, a very important class of formulas is those that are true irrespective of the truth values we assign to the propositional variables, namely the tautologies, namely those formulas that are true by virtue of logic alone, irrespective of their interpretation. And in predicate logic, we have the same idea. There's an important class of formulas which are true by virtue of their logical structure alone. And we can formulate that in a mathematical definition as saying we'll designate a formula as being true by virtue of its logical structure alone, if and only if, well, but in the case that it's true in all structures. So we replace the notion of interpretation of variables by truth values with structures, okay? With propositional variables by truth values with structures. And it really is a more general notion because propositional formulas are included in predicate formulas, and propositional variables, we would include them by having zero array relation symbols for the variables. Okay, so let me make the definition. So a formula is said to be valid, logically valid, but often just valid. It's the same terminology we use in propositional logic, valid, although in propositional logic we also use the word tautology. In predicate logic we tend not to use the word tautology. It's the same idea. If it's true in all structures. Now, because a formula with 3 variables requires an environment to interpret it in, we should say for a general formula if it's true in all structures and all environments. But in order to keep things concise in this lecture, I'll just talk about sentences. So a sentence. Well, maybe let's just make a remark here. So a sentence has no 3 variables. So for a sentence 5, whether or not so we might look at whether a sentence holds in a given interpretation of variables, environment interpreting variables in a structure M. But the sentence has no 3 variables, and it turns out it's irrelevant what row is here. Because here with the idea of row, the important role it plays is to give values to the 3 variables of the formula. Here there are no 3 variables, so this turns out to be irrespective of the value of row. Is irrespective or independent, let's say, independent of row. So we can just write, we simply write that for a sentence, and we've got a sentence on the right, we can simply say sentence is true in the structure. Okay, so like our sentence for commutativity is true in this. It's either true or false in the structure. The important thing is we quantify over all the variables. But still, the environments are needed to define the notion of satisfaction, because in order to define satisfaction for the quantifiers, we start to need to, we do work with situations in which the formula becomes, here, this is no longer a sentence because we've removed the quantifier from it, and the environment plays a crucial role in these clauses for the satisfaction relation. Anyway, so a sentence I is valid, this is the definition, if for all structures and really so all structures satisfy the sentence. And then we can make a connection similar to the connection, well, exactly parallel to the connection we made in propositional logic between our semantics, that's the meaning of predicate logic, defined in terms of structures and satisfaction, and the proof system, the natural deduction proof system we introduced in the second lecture of the course, or whichever lecture it was. And we have exactly the same theorems that we had for propositional logic, the soundness and completeness theorem. So the soundness theorem says for any sentence, So I'm just going, I won't write the sentence, but if a sentence phi has a proof, by proof, I mean a proof with no undischarged assumptions, just like in propositional case. I won't write that down now, but I've said it in natural deduction. Then phi is valid. So just like propositional logic, we can only prove tautologies. The whole point of the proof system is we're trying to reason about things being true by virtue of logic. That's the point of reasoning. And so the proof system is correct. We can only prove valid sentences. But moreover, just like in propositional logic, there's a much deeper result, which is that the proof system is complete. So that is, if phi is valid, so if phi is true by virtue of logic alone, then it has a proof. It has a, let me write like this, an ND standing for natural deduction proof. So these are very nice results tying, we have the semantics of predicate logic saying what formulas mean, giving interpretations to the syntax. And we have these two theorems saying that our proof system, the formal rules we've got, precisely align with that semantics. Soundness is basically you show that all the rules are only making correct logical steps. And so somehow by induction on the length of the proof, you can establish that every proof is valid. It's a little bit more involved with that, but that's the idea. The completeness theorem really does require a proof, and this was not in the context of natural deduction proof system, but in the context of a different proof system. This was the first major contribution that Gödel made to mathematics, was establishing this completeness theorem for predicate logic. So it's not a difficult result by today's mathematical standards, but it's not a triviality, and it's a very important result. Okay, so that sets the background on predicate logic. We know how to interpret our syntax, and we know that the semantics that we have for interpreting it, the syntax in terms of structures, precisely aligns with the proof system. And now we can consider algorithmic problems for predicate logic. And just to say, we've got the notion of validity. We can also define the notion of satisfiability. So a sentence phi is satisfiable. And what do we mean in this case? Well, as I said, our structures are taking the place of assignments of truth assignments to the propositional variables. So a sentence phi is satisfiable if there exists a structure such that satisfies the sentence. So satisfiability was an important algorithmic problem in propositional logic. Maybe it's an important algorithmic problem in predicate logic. But let's see how we can deal with it computationally. So let's start actually with validity. I mean, there's a close relationship between validity and satisfiability, the same as in propositional logic, that a sentence is satisfiable if and only if its negation is not valid. So we have exactly the same interrelationship between the two notions. So can we have a computer application that we input a sentence and it gives us back an answer yes or no, depending on whether the sentence is satisfiable. So let's say the valid first. So the validity problem. So as we're going to construe it, the input is a sentence by over a particular signature, and the output is yes if by is valid and no otherwise. So for many reasons, it would be very nice to have an efficient algorithm that would do this. It could solve a lot of open mathematical questions if we did this. But the famous negative results, so this was essentially asked as an open question by Hilbert in the 1920s. He called it the Entscheidungs problem, and or not we can solve this problem. And it was answered very famously by Alan Turing and also Alonzo Church in 1936. So the theorem Church, but they work independently. Turing 1936. The validity problem is not decidable, so it's undecidable. Hands up if you know what undecidable means. Okay, not everyone. So it means not decidable. So decidable a yes-no problem is decidable if there is some algorithm, is an algorithm for it that is guaranteed to terminate with a yes or no answer as a predicate. The point is, it terminates, if the answer is yes, it will terminate and tell you yes, and if the answer is no, it will terminate and tell you no. So for it that it's guaranteed to terminate with the correct answer, correct yes or no answer. Okay. So one can't use an algorithm to say to solve such a problem is a formula valid, and because of this, we also can't solve the satisfiability problem. There's also undecidability. It's also undecidable because if we can solve the satisfiability problem, we can solve the validity problem by giving the negation of the sentence to the satisfiability problem, and then negating the answer that we get. So it follows that the satisfiability problem is also decidable. Okay. It's been disappointing. I mean, over the set, we don't have the propositional set. We don't have any algorithm we don't know any algorithm that's efficient theoretically in having polynomial time worst case behavior, but we do know some practical algorithms that work quite well. We're actually beginning to know some practical algorithms that work quite well for this problem, namely good a little bit more dedicated large language models and beginning to sort of be able to approach, not to decide it, of course, but to provide reasonable answers to this problem. But the problem that we can solve efficiently, that is actually very useful. So, I mean, basically, the point of in this hour, I'm going to like consider a whole range of. So this basic problem that we had for propositional logic satisfiability, that's no good for us without changing it. So what we're going to consider is just a range of different things that we can or cannot do algorithmically. We're going to see what the situation is. Then in the next hour, we're going to focus on one particular one, which is the one that's related to the ally analyzer that people are going to present in 3 weeks' time. So, an algorithmic problem that one can deal with, that's very useful. But a practical algorithmic problem is the following. So the input is a formula or a sentence. I mean, there are always versions of these problems for formulas and also ones that involve there being some theory in the background as well. But I'm just going to give the simplest formulation for problems. Yeah. So now the input is sentence phi and a purported. Hands up if you've heard the word purported before. So it's like something that is claimed to be something, but you don't know whether or not it is. So we're going to have a purported ND natural deduction proof of phi. So the idea here is, somebody says, I am proving phi, and here's my proof of it, written in natural deduction. But, they might be fibbing. They might say, here's my proof that of the implication, the axioms of mathematics, namely ZFC set theory, implies the Riemann hypothesis. And you want to be damn sure they then give you a 100-page script with a natural deduction proof in it. You want to be damn sure that they're not fibbing, that this is a correct proof. So the output is yes, if the proof is correct. If it's a correct if it correctly follows the natural deduction rules, and no otherwise. In practice, you can have some more interesting information otherwise, like it tells you what the error is, or something like that, but we'll just deal with the yes-no question here. And this algorithmic problem is efficiently solvable. So this is actually very useful. And it's efficiently solvable because the rules of natural deduction are, every rule says, well, in order to apply this rule, you need some assumption in this position, and then in the proof we then remove that assumption from the future proof by sort of putting a metaphorical box around that part of the proof, and then we can never refer to that in the future. And all the rules that we have for formulating the proof can be they're algorithmic in nature, so they can be checked by a straightforward algorithm. So this is a practical and efficiently computable problem. And this is useful because this is the basis of what people call proof checkers or proof assistants, which is a class of technologies that, you're going to be dealing with on the practical side of this course. And you may have used on other courses. So it's a class of technologies that support constructing formal proofs of mathematical statements, and the proof assistant checks that your proof is correct. Moreover, it's much more helpful in that it also helps you construct that proof. But the algorithmic basis of it is that you can check that proofs are correct, and that's this fact that it's a practical and efficiently computable problem. So this is used in proof of systems, computer proof of systems. It's like computer. Okay. Now that could be a whole lecture in itself, but I don't really want to dwell on too many of these problems, so let's go on to the next one, which is to revisit validity in the light of this. So we've seen that validity is an undecidable problem, but we know there's actually an algorithm for it. Now, what's wrong with this algorithm? Consider the following algorithm for validity. So input sentence fine. And the algorithm is systematically search the space of all proofs, because proofs can be written in ASCII syntax or something Unicode syntax, so ASCII is very old-fashioned. Anyway, it can be written in syntax and submitted to a proof checker. So let's systematically search the space of all potential proofs. And when we've got a candidate proof, we check it to see if it is a proof. And if it's not, well, we go on and look at the next proof. So systematically search the space of all proofs until we find all proofs, until we find the proof of phi. By which I mean a proof with concluding formula phi. And if we do find the proof of phi, we return yes. Or actually, if we want to be more helpful, we actually return the proof itself. But anyway, we're looking at yes/no questions. So if we find such a proof, then yeah. Okay. So why does this not? So this is an algorithm, you can implement it. Why does it not contradict the decidability of validity? Yeah, it might run forever. I mean, the way I've written it, it will never return no. And it's going to be very hard to make it return no, because when would you return no? At any point, you've not yet found a proof of phi, but how do you know that, it might just be around the corner? You need to search a bit, you never know when to stop. And in fact, the Church-Turing result is a mathematical proof that there's no possible way that you can ever always know to stop. Okay, so there's no way we can actually build a no feature into this. So this does not solve the decidability, this does not amount to what's called a decision procedure for the algorithm. It does not always return a yes/no answer, but it provides something called a semi-decision procedure. So this algorithm shows that validity is semi-decidable. And the problem is, well, just hands up again if you've met the concept of semi-decidable before. Okay, basically, the same people that have met decidable have met semi-decidable, the same people that haven't. So a yes/no problem is semi-decidable. if there exists an algorithm that always correctly answers yes, answers yes, if the answer is yes. That runs forever otherwise. It doesn't tell you no. So, okay, there's not clear how useful such a thing is. Also, if you implement this actual algorithm, then the search space is so gigantically huge. I mean, you know, every possible step, you've got lots of choices for rules you might make, and that's immediately leading to an exponential blow up because you're searching paths down through essentially a finitely branching tree. So in practice, such an algorithm doesn't just not halt with no, but it also doesn't halt with yes, because, I mean, not in practical time, because you have to wait too long for it. However, the fact that this is semi-decidable is important, because this is the basis of theorem proving. The goal of, so there's the proof checker, where the proof assistant, where you together with the computer come up with a proof. It helps you to do it, and at the same time it checks that your proof is correct. But you're making a lot of input into that. But then there's also the idea of an automatic theorem prover, where instead you want it to do the intelligent work for you. So you just put in the sentence 5, and you say go ahead and prove my theorem 5 for me. Well, prove my statement 5 for me, and turn it into a theorem, and it goes ahead and tries to find a proof. And this is important because the semi-decidability of validity is the basis of automatic theorem proving. The theoretical basis of it. I mean, of course, the interesting, there's a lot of interesting, huge amounts of very interesting work in automatic theorem proving that then is trying to actually do something with this very, very combinatorially challenging problem of trying to look for proofs. The basis of automatic theorem. Okay, so what about satisfiability? Is that semi-decidable? So I'm going to clear the board. So here we're trying to say, does there exist the model rather than is it true in all models? Does there exist a structure rather than is it true? So does anyone have an opinion on whether satisfiability is semi-decidable? So I want to say phi is phi, the question is phi satisfiable? So we can input not phi into a validity checker, and we want to get the answer no out from the validity checker. And then we can say yes, phi is satisfiable. So do you think? The problem is, yeah, we can't get the answer no out from the validity checker. The same algorithm here gives us an algorithm that we can turn it into an algorithm that, given the sentence phi, will answer no if a formula phi is unsatisfiable, but will run forever if phi is satisfiable. So satisfiability is what's called co-semi-decidable. And for co-semi-decidable, well, it would be better to use a different colour. You simply reverse the roles of yes and no. So we have an algorithm that will always give us a no answer, but will run forever on a yes answer. So let's put that in red. Correct, the answer is no. If the answer is no, that runs forever otherwise. The satisfiability is a co-semi-decidable problem. So that's not very useful. We want, and there are situations in which we really do want to know if a sentence in predicate logic is satisfiable. And a common scenario for that is we might use sentences in first order logic to formalize some scenario we're interested in. And we want to, and the properties we're stating will be constraints on the scenario. And the question of satisfiability is, can we satisfy these constraints? Because maybe we've added too many constraints and some of them are inconsistent with each other. And so, to answer questions like that, it would be good to be able to have some algorithmic handle on the problem of satisfiability. And it would be particularly useful if actually we could, in showing that problems, our constraints are satisfiable, if we submitted that to a checker, it might not just say they're satisfiable, but it might actually come up with a structure that satisfies them. In which case, we're probably interested in getting a finite structure back, because they're computationally much easier to deal with than infinite structures. So then there's the question of, can we deal with finite structures? Could we, is it an interesting question to say, we've got a scenario captured by a formula phi. Can we satisfy this scenario by a finite structure? And this is called finite satisfiability. So that's, for finite satisfiability and something related to it called bounded satisfiability are the two main problems I want to look at in the rest of the lecture. But first, to give you a flavour of the kind of scenario that I have in mind, I'm going to present such a scenario so we've got, so it's not just an abstract talk about scenarios. It's very, very simplistic, this scenario, but it should give you hints at the kind of thing you can do. So we're going to use predicate logic to model a very, very simple computer network. And maybe this will take us up to the break, and then you can think about questions, but they're not deep questions that I'm going to ask. But just as an example of the sort of style that one can use predicate logic on. So modeling a terribly simplistic computer network. So we're going to have a signature that actually in this case is just going to consist of relation symbols. The signature so I'm going to have binary relation connected. So I'm going to write the arities like this. I put a slash and then say what the arity is. So it's a binary relation, so connected to predicate of arity 2. And the idea is the elements of our structure are our computational devices. and connected of X and Y holds if X and Y are connected to each other by a cable, if you like, or by some other means, but it doesn't matter, it's just connected. And then we're going to have two unary predicates, a server and client, server and client. And these are, as I say, unary predicates, meaning they take one argument. And I'm going to put the constraints on our situation as a set of axioms, saying, it's not just, we're not interested in any structure that has a binary predicate and two unary predicates. We want them to behave a bit like servers and clients that satisfy some connectivity rules that we're going to impose. And it's just for illustration purposes. So we're going to say that for all X, so no device is connected to itself. So connecting is a relation that holds between other devices, between different devices. All XY, that's for all X, for all Y, strictly speaking, but obviously likes to use shorthands. If X is connected to Y, then Y is connected to X. So it's a symmetric relation. So basically, connectivity is a graph in the usual simple sense of graph. And now we want to say our universe consists only of servers and clients. And in this particular network that we've got, a device is either a server or a client, but not both. So for all X, either X is a server or a client. And for all XY, for all X, it's either the case that X is not a server, or it's the case that X is not a client.
Excuse me, X.
Yeah,
Client X.
thank you.
Of client X.
Indeed. And we're going to require that every server is connected to some client, and every client is connected to some server. So we can do that. So here we're making more substantial use of the quantifiers. So for all X, if client is an X, sorry, if X is a client, then there exists a Y such that server Y and connected XY. And for all X, if X is a server, then there exists a Y such that connected Y and there exists a client. There's a client that X is connected to. Client Y. Y. And lastly, we have an axiom saying that servers only connect to so I put them in different order. So 1, 2, 3, 4, 5, 6. Yeah. Good. Found it. So the last one says that servers are only connected to clients, so we don't connect two servers to each other. So X and Y are connected, then it's not true that X is a server and Y is a server.
Do we also need the for all here?
We do, thank you, for all x, y. So often when one writes a list of axioms like this one omits the universal quantifiers. But you know, just to make it clear that these are sentences, I'm writing them. So it's not x is not a server and y is not a server. Okay, and so this is like our axiomatic setting, and then we want to. So it's clear that it's very easy that this is satisfiable. It's very easy to come up with little models of this, but we might be interested in some more subtle questions. So, for example, we might be interested in questions like, and this is the one in the notes, so is it consistent to have a network with 10 devices such that only 2 are servers. Such that exactly 2. I mean, yeah.
But doesn't the last axiom permit that 2 clients are connected?
2 clients can be connected.
Two clients can be, okay.
Yes, they might
Sorry.
they might be networking with each other or something like this, but servers only serve clients, they don't serve each other. That's the idea of this model. I mean, as I say, it's very simplistic and it's also very what's the word for it? I'll think about what the right adjective to describe it is during the break. So what I want to show you is now technology that can allow us to answer questions like this in a nice way. It's not a deep question in this case, but it gives a simple illustration for you to think about. So in the break, we don't have a break now until 10 o'clock. In the break, you can think about this question yourselves, and I shall think about what the adjective I'm missing in English is to explain. Okay, good. So have a great till 10 o'clock. Okay, so we want to translate this into a satisfiability problem. So one way of saying this is we want to satisfy the sentence that's the conjunction of all of these, together with a sentence that expresses this, which can be expressed as a sentence in person with the logic, but a bit complicated. So we want a network with 10 devices. So we want there exists x1, there exists x2, x3, up to x10, such that they're all different. So they're all different is a conjunction over all pairs of disjoint ones of these, saying they're not equal, so the negation of equality. We can write that, we'll use this sort of notation for multi-parity conjunctions. So this is like a much longer formula if one telescopes it out, but it will count from I is 1 to 9, and J goes from I plus 1 to 10. Or I'll just write xi is not equal to xj, but formally that's the negation of xi equals xj.
Do we have to input this in the signature, or is this something that is equality or not equality is always present?
So equality was included in today when I wrote out the formulas, at least it was supposed to be. I hope it was. Was it?
No. For terms, yes.
The terms, yeah. So variables are terms, yeah. And then this is just the negation of such equality. And we also want, well, oh goodness me, and when there exists X, there exists a Y such that for all Z, if server such that X is not equal to Y, and for all Z of server, if Z is the server, then Z equals X or Z equals Y. And they're both servers. With that first, so there exists X and Y that's both servers, they're different, and for all servers are equal to 2. Anyway, so it's a complicated statement. That's not logic, but it can be.
But this doesn't reverse that there are exactly 10 classes. There are at least 10 classes from this.
Very good point. So we could indeed add a bit more to say there are exactly 10 devices, but everyone should leave the formula like this at the moment. But that's an excellent point. But the idea is.
Sorry, don't we get that there are exactly 10 because we have the inequality? Like those
the
two big wedges.
It says there are at least 10. But there could be,
right. Yeah.
there could be other things in the universe. But let me put in at least as well, because I mean, you can think of it as two different periods. This is the at least one, but we might be interested in exactly 10, which we can extend the query, or we can get to exactly 10 in a different way, which we'll do later.
It's at least 10 devices, but exactly.
Oh, thank you. Aha. Good, I didn't even say exactly 10. So
Okay, I read it.
yeah. But anyway, there are two variants. This is a good point. So we'll have so one variant with at least, and one is with exactly. And this sentence here says at least. Oops, at least. Okay. And the idea is, you know, what one would like is we want to know whether this is satisfiable in conjunction with this. So we present the conjunction of all these sentences to a satisfiability checker, and we want it to try and find us a model, a structure of these sentences, and to actually return the model to us. The problem is satisfiability is co-semi-decidable, so we don't have an algorithm for it. But it turns out we do have an algorithm for finite satisfiability. So satisfiability by a finite model. The finite satisfiability is the question, is the problem. The question is a formula phi, a sentence phi, yeah. And the answer that we want is yes, if there exists a finite structure, then such that finite just means its underlying set is a finite set, and no otherwise. So that's the problem. And again, it's not a decidable problem, but in now, so whereas satisfiability was co-semi-decidable, finite satisfiability is a semi-decidable, not co-semi-decidable. So theorem or proposition, well, let's just write it and underline. So finite satisfiability is semi-decidable. So we do have an algorithm, if you remember the definition of semi-decidable, we do have an algorithm that in the case that before the sentence is finitely satisfiable, it will always correctly answer yes. But in the case that it's not finitely satisfiable, it will run forever. And moreover, it's better than that because we had this distinction last week between SAT solving and I think what I called useful SAT solving, where the useful SAT solver actually provided a satisfying assignment, as well as just saying, yes, it's satisfiable. And we get useful finite satisfiability. So in fact, we have an algorithm. We have an algorithm for, let's write it in green, useful finite satisfiability. The useful finite satisfiability doesn't answer yes, but, well, it does answer yes, but the useful one, just like this useful satisfiability, it gives you more information. In this case, it outputs the finite instance, thus outputs such an M. So it actually finds a model M and outputs it. Okay. And I'm going to very briefly outline why this works. And it's it's nice that we have an algorithm, but the problem is it's once again a very disappointing, inefficient algorithm that you're never in practice ever going to try to run an algorithm like this and get anywhere with it. Because what do you think we can do with finite structures? Well, if you look at structures of size, I mean, normally you don't, I should have said when I defined structure, normally you require the set M to be non-empty. So we look at first at structures of size 1, and then there'll be a finite number of non-isomorphic structures of size 1. So we consider all of those. Then we look at structures of size 2, and there'll be a finite number of non-isomorphic structures of size 2, and we consider all of those. And then structures of size 3, and so on. But very quickly, the number of structures of size, even 5, say, of non-isomorphic structures very quickly balloons, so explodes. So, for example, part of this is just that the relation connected is a graph, and the number of graphs of size n, it grows very, very fast. So it's completely unrealistic, but basically it works like this. For every size n, from 1, 2, 3 onwards, the algorithm systematically considers enumerates all non-isomorphic structures of size n, which is also, as well as there being very many of them, even testing for isomorphism is also something that one doesn't know how to do very efficiently. So we enumerate all non-isomorphic structures. And by that I mean we want one structure from every isomorphism class of structures of size n. for each, we look at for each structure M, we look at the model checking problem. So we simply, for each structure M, we simply test it to see does phi hold in M. So we test the property phi in the structure M, and if and when we find one that satisfies phi, we return that structure M. This is called the model checking problem. If and when we find such a structure, we turn the structure M. So this model checking problem, the input here, the input for this is a pair, and phi, where M is a finite structure, and phi is a sentence. And the output, in this case, we want an actual decision procedure. The output is yes if M satisfies phi, and no if M doesn't satisfy phi. So output, yes if M satisfies phi, no. The model checking problem is simply you take your finite structure, you read the you go through the formula phi, you break down its structure like it, and you recursively test the satisfiability. So if phi is a conjunction, we phi 1 and phi 2, we break it down into phi 1 and we recursively test to see if phi 1 is true, and we recursively test to see if phi 2 is true. If phi is an existential quantifier, we then go into a for loop that will check that is a for loop that instantiates the variable x with every element of the structure M, and we'll check for each element of the for loop whether or not phi holds for that. Sorry, for each element of the structure, whether or not phi holds for that structure. And the universal quantifier is also a for loop. Just for the universal quantifier, you want to check that it holds for all elements, and the existential quantifier, you check that it holds for one element. But the point is, this is done, the model checking is done by algorithmically checking the definition of satisfiability, checking that M satisfies phi according to the definition of satisfiability. In terms of like how inefficient all the problems are that we've been considering, this is relatively efficient in that the amount of time it takes is proportional to the size of the sentence, together with k to the power of d, where k is the number of elements of M, and d is the depth of nesting of quantifiers that we get in this formula. So the point is, we nest quantifiers like for all x there exists a y such that for all z, for all w, that would be a nesting of 4 quantifiers. Then you've got 4 nested for loops there to do the checking, and so the time complexity is going to each for loop will go over the number of elements in the model. The time complexity will be that to the power of the d, which is the depth of the quantifier. So this is the quantifier nesting. So this is done in more details in the notes, but I don't want to spend time on it now because I want to go to the main thing that I wanted to come to, and that's, you know, basically still, you won't find a software tool that implements this because this is just combinatorial, it's just a disaster. There's no hope of getting anywhere with enumerating all structures. So finally get to the one, well, no, we had one problem earlier, which is really algorithmically solvable, which was the proof checking problem. So checking that a proof is correct. But we now get to the other problem that can be addressed in practical tools. And that's we modify finite satisfiability to what we call bounded satisfiability, which is the natural modification. And so bounded satisfiability is, again, we want to say, is a sentence finitely satisfiable? But we're going to give a bound to the size of the structure that we're interested in. So now the inputs, and when I say question, the input would have been a better word. So now that the input is a sentence phi, together with a bound n, is a natural number greater than 0. And the answer is yes, if there exists a structure that n satisfies phi, but also the size of the structure, so the set of the underlying set of the structure has size less than or equal to n. Okay, so we're searching for a model with a bounded size. Okay. So we could, again, try to do this the same way, and we just stop when we get, well, once we've checked all models of size 1, 2, 3, all the way up to our size capital N, we then stop the algorithm, and we can then actually improve this algorithm because it's now decidable. We can then say no at the end. But this is still impractical because it's still using the same blind search over arbitrary models of the same size, okay? So over non-isomorphic models of each size. So that's not possible. I mean, that's not feasible. So we're going to do a different approach. But just to remark that doing that approach, we know when to stop. So this algorithm, so this problem is decidable, but not efficiently decidable. This problem is decidable. So we do actually, in theory, have an algorithm that answers yes if it's satisfiable, with a model of size at most n, and no if it's not, because we check all the models, we check all models of at least one element of each isomorphism class for each model up of size up to n, and then once we've checked all that enormous number of models and not found an example that satisfies the sentence, then we can correctly say no. Okay. So now we can see how we can solve our question with exactly 10, yeah, using this query. So let's make the question exactly 10 by using the conjunction of these axioms together with this axiom. We're going to do bounded model checking with bounded model checking on. Let's use T for the conjunction of these axioms, meaning the theory, and Q for this axiom, meaning the query, and we do bounded model checking on T together with Q. So I mean conjunction of all these, well, let's say T and Q, with bound N equals N. Okay. And we do that, for example, in the alloy analyzer, and it computes for some length of time, and then it comes back with a picture like this. So C means client, S means server, and we'll find out that it is indeed finitely, it is indeed satisfiable. So there does indeed exist such a network. Okay, so that's one example. And if you're not happy with the network it's found, then you can run it again and you'll get maybe a different network that satisfies the same thing. So that's the kind of thing you can do with the alloy analyzer. Well, actually, I haven't tried out this example on the alloy analyzer. I somehow suspect it wouldn't work because in most things I've played with on the alloy analyzer, 10 is too large a bound to use. So so I'm going to talk about how it works, but it tends to work for smaller numbers 10 rather than the 10 itself. But some people are going to talk about the alloy analyzer in 3 weeks' time, so we'll see examples of that. Okay. Yeah,
As a question.
you can ask a question, then yeah.
Like, it seems to me that we could make this more efficient by just like requiring a model to just be of size 10, and then we actually don't need to specify in formula that we want exactly 10 elements. We just check.
Yeah, we can probably do that.
Yeah,
yes.
because the algorithm is just going to go, okay, 1 doesn't work, 2 doesn't work, 3 doesn't work, and it will.
Well, no, but this algorithm would do that, but we're not going to. But the algorithm is going to be completely different. So now I want to talk about the algorithm. So the point is, this algorithm would be hopeless. This wouldn't even work for like n equals 3. This kind of algorithm, because there are just too many non-isomorphic copies. So we want a better algorithm, and so what I want to do is show you the actual algorithm for bounded satisfiability, which is to reduce bounded satisfiability to a SAT problem, a propositional SAT problem, and then submit it to a SAT solver. So this is how the tool alloy works. It doesn't use exactly the reduction that I'm going to sort of use a better reduction than I'm going to say, but I just want to get the theory across. Okay, we've got 20 minutes. So maybe I'll do the main step and then we'll see. So this, I mean, there's the main idea we can cover in detail, and that's really the important thing to get across. So the notes this week have more detail than are in the lecture. So that detail is there for, your information, if you like. But when it comes to the oral exams, you're expected to understand things more or less at the level of the detail that's considered in the lecture, rather than, if you know what's in the notes, that's in addition, that's great, and that will certainly help your understanding, but you're expected to understand what was in the lectures in detail. And the reason the notes have more information is I used to do this lecture and a half on this material, but this year in order to have the student presentations, I'm instead covering material a bit less in depth, that able to cover more material in total, of course. Anyway, so what we want to do is we solve bounded satisfiability, bounded satisfiability for predicate logic, satisfiability by reducing to the propositional sample. And to do this, I'm going to assume that we don't have equality in the language, which we did there, and that we don't have function symbols, which we didn't there. But there are then techniques one can do to deal with equality and function symbols on top, which are in the notes, that for the lecture, we'll just deal with the case with no function symbols and no equality. So we assume phi does not involve function symbols and equality. So the input formula is phi, the input sentence, and the bound is n. And what we're going to do is we're going to translate the input sentence into a formula of propositional logic. So to do that, so we create a formula in propositional logic. Hang on, well, let's do it right. Does not involve function symbols except constants. We are allowed to have constants. So actually, before creating the formula in propositional logic, is we add n constants, C1, C10 to the signature. The idea is these are going to play, these stand for elements in the structure that we want to come up with. Now, the structure has size at most n, but in the case that it's a smaller structure, some of C1 and Cn can stand for the same element. Okay, they can designate the same element. And now for each predicate symbol, the variety n, we add propositional variables which we'll call P let's make this K just so we don't have a conflict of n's. So we add a propositional constant for a propositional variable for each tuple, each k tuple of I1, ik in n. Okay, so the idea is we're going to be looking at structures that have at most n elements. We'll name the elements C1 to Cn. And this propositional variable is a propositional variable that's its role is to assert that the relation P holds for the tuple of elements indexed by the n tuple I1 to ik. So each of these is a number, sorry, yeah, belonging to n. So this is in the set from 1 to n. Okay. So each of these is a number from 1 to n, and this is saying P holds for this k tuple of elements. So if it was 3 fill 6, then P would be a ternary predicate, and it would be holding for the element C, the tuple of elements C3, C4, 3, C6. So we're simply giving numbers to talk about, we're simply numbering the elements of the finite structure. And we define a mapping So since I've got phi as my starting formula, I'm going to change this to psi here with a mapping psi to psi star from sentences in our extended signature with the constants to propositional formulas using the above variables, propositional variables, using the propositional variables. And the way this translation works is what we want is that this formula on the right is satisfiable if and only if this formula on the left is satisfiable. And moreover, a satisfying assignment here tells us how to build a structure that satisfies the first order formula on the left. So it might sound a bit complicated, but when you see the translation, it's actually the translation itself, which I'm writing with this star, explains a lot how this works. So we had a seminar at the Foundations seminar in FMF from the Maths department here recently, in which the speaker at the seminar was somebody introduced the translation like this involving a star, and Andre Bauer made the point that logicians are very unimaginative in the name of the translation. So often you get a translation on formulas and you call it star. So this is probably one of many examples we're going to have of star translations, as they're called, where we translate formulas from one logic to another by applying a star to it. And the idea is we want to, as I say, be able to check the satisfiability of psi, the first order formula, by checking the propositional satisfiability of psi star, and from a satisfying assignment to the latter, get a satisfying assignment to the former. So let's start with the main case. There's an analogous case for all, but if we've got an existentially quantified, so this is a sentence, we want to translate this to a propositional formula that's going to be whose satisfying assignments are in one-to-one correspondence with structures that satisfy this formula, structures of size at most n that satisfy this formula. So there exists an x phi, well, that's saying phi holds for the up to n, capital N, different elements we have in the structure. So what we do is we consider phi, the sentence phi, where we replace x with the constant C1, and the sentence phi where we replace x with the constant C2, all the way up to the sentence phi where we replace x with the constant Cn. It should indeed. I had just realised that myself. So, and we want there exists an x such that phi holds. So we want at least one of these to be true. We want to translate this to a propositional formula. This is a first order formula in which we've got rid of the one quantifier, and we've substituted for it a constant, so we're keeping it a sentence. And we simply translate all of these. So the translations, so we recursively perform the translation on these inner formulas. And then if we've got a conjunction, oh, sorry, I should really be using phi because phi is our goal at the start. So let's turn all these phi's into psi's. If we have a conjunction phi, psi1 and psi2, then we simply we need to solve psi 1, and we need to solve psi 2, and similar for the other propositional connectives, yes?
Why exactly do we need this constant?
Now, because what I'm doing is I'm translating a sentence to a propositional formula. And when I've got a quantifier, if I take the quantifier off, then I don't have a sentence anymore, because we've now got a free variable, x, in here. And so we can't really do anything with that, but the point is I want to instantiate that variable because we've got an existential quantification. I want to instantiate it with the up to n potential elements of the structure. So I use the constants for that, and because I'm using a constant, I get back a sentence, so I can continue with the translation. Okay. And the last, there are similar things for the other propositional connectives. The universal quantifier is the same, except that you replace the disjunction with a conjunction. And lastly, for a predicate symbol, if you've got P, well, so a predicate symbol will have an arity, K say, and because it's a sentence, the predicate symbol will be in, so that's called as I1 to IK. The predicate symbol for an atomic formula to be a sentence, we don't have any function symbols. The only things we can have as the arguments can be constants. So we've got k different constants here. Each constant is of this form, C1 to CA. So for each one, we have an index, I1 to IN, which is a number between 1 and n. They may be repeating indexes. And this we translate, the whole point of this was to translate this to the propositional variable P, I1 to IK, which is the reason that these propositional variables were introduced. And the crucial fact is satisfying assignments for psi star are in one-to-one correspondence with structures of size less than or equal to n that satisfy psi. Yes?
Brackets and stars, here keep the translation.
Ah, yeah. Thank you. Because we're defining the translation. Yeah. Very good.
Also, in the first line, it should probably be psi's on the right side.
They are psi's on the right side.
Okay. Yeah, no, they look a little bit like pi.
I haven't deleted as much as I should, but I was converting phi's into psi's, and then if there are any Greek people in the audience, they'll probably be hating what I'm doing with our alphabet. Okay, I think that's a good place to leave it for today. There are lots of statements being made today that I've given you ideas for the algorithms, but theorems don't have proofs. So, for example, the completeness theorem, the Gödel completeness theorem, and here I'm just making a claim that these satisfying assignments are in one-to-one correspondence. I'm not proving that. When you understand the translation, you can kind of see it's true for yourself. But as I said, in the oral exams, you don't need to understand. You essentially need to understand the material at the level I presented it in the lecture. So we're not going to go into formal proofs of these kind of statements. Okay, good. So that's it for this week. Are there any questions? Right, so have a nice week. If anyone from the team for next week is here and wants to discuss with me, I'll be happy to.